Welcome back to educator.com and welcome back to linear algebra. Today we're going to talk about matrices. Matrices are the workhorses of linear algebra. Essentially everything that we do with linear algebra of a computational nature, when we're not necessarily discussing the theory, is going to somehow use matrices. You've dealt with matrices before. You've seen them a little bit in Algebra 2 if I'm not mistaken. You've added, you've subtracted, you've maybe multiplied matrices. Today we're going to talk about them generally, talk about some of their properties. We're going to go over addition, we're going to go over scalar multiplication, things like that, the transpose of a matrix. So having said that, let's just jump right in and familiarize ourselves with what these things are and how they operate. Okay, so the definition, a matrix is just a rectangular array of mn entries arranged in m rows and n columns. So for example, if I had 3 rows and 2 columns matrix, the number of entries in that matrix is 3 times 2, 6, because they're arranged in a rectangular fashion. That's all this mn means. So most matrices will be designated by a capital letter, and it'll look something like this. It'll be symbolized most generally A11, A12, ... A1n. Notice it's very, very similar to the arrangement that we had for the linear systems. And of course, there is a way in a subsequent lesson to represent the linear system by a matrix, and we'll see what that is. So A21, excuse me, A22, ... A2n, and we'll go down, This will be a M1, a M2, ... a Mn. So the top left entry is A11, bottom right entry is AMN. This is an M by N matrix. This M is the rows, sorry. The rows always come first. This is the row, and the N is the column. So m rows, n columns, which is why this first subscript here is an M, and this second subscript here is an N. Okay? Basic example, so something like 1, 5, 6, 7. Oh, a little thing about notation on matrices. You're going to see matrices represented a couple of ways. You're going to see it with these little square brackets. You're going to see it the way that I just did it, which is just 1, 5, 6, 7 with parentheses like that. And sometimes in this particular course, probably not in your book, but in this particular course, oftentimes when I write a matrix, I'll arrange it in a rectangular fashion, and it'll be clear that it's a matrix because we'll be discussing and talking about it as a matrix, but I often will not put the little parentheses around it. Don't let that throw you. There's no law that says a notation has to be this way or that way. These are just conventions. As long as we know what we're talking about, the notation for that is actually kind of irrelevant. Okay. So this is a 2 by 2 matrix. There are 2 rows, 2 columns. You might have something like 3, 4, 7, 0, 6, 8. This is going to be 3 rows, 2 columns. So this is a 3 by 2 matrix. You might have something like this, which is a 1 by 1 matrix. A 1 by 1 matrix is just a number. Which is actually an interesting notion, because those of you that go on to study some higher mathematics, perhaps even complex analysis, as it turns out, numbers and matrices share many, many properties. We're actually going to be talking about a fair number of those properties. So the idea of thinking as a number as a 1 by 1 matrix, or the idea of thinking of a square matrix as some kind of a generalized number, it's actually a good way to think about it. So. Not really something that we're going to do, but it's something to think about, maybe in the back of your mind if you're wondering, wow, they seem to behave kind of similarly. Well, there's a reason they behave similarly, because numbers and matrices, their underlying structure, which we're going to examine later on, is actually the same. Okay, So we speak about the ith row and the jth column. So let me do this in blue. We talk about the ith row. We talk about the jth column. So remember the ij, this was the notation. This refers to the row. This refers to the column. So if you have something like A57, we're talking about the entry that's in the 5th row and the 7th column. Just go down 5, go over 7, and that's your entry. Okay. The third, well, let's actually do a specific example here. Let's say we have a matrix A, which is 1, 2, 3, 4, 7, 9, 10, 4, 6, 5, 9, 6, 0, 0, 1, 8. And they can be negative numbers too. I just happen to have picked all positive numbers here. So we might talk about the third row. That's going to be this thing. So you have 6, 5, 9, 6. We might talk about the second column. The second column is going to be that, 2, 9, 5, 0. Okay. A 1 by n matrix or an m by 1 matrix. These are just single columns or single rows. You can arrange them any way you like. So a 1 by n would be something like this. If I took, let's say, the 4th row, I would have 0, oops, see these lines showing up. We don't want that. Now let's do it over here. So if I take 0, 0, 1, 8, this is 1 by n, in this particular case 1 by 4. Or if I take, let's say, 4, 4, 6, 8, this is a 1, 2, 3, 4, 4 by 1. In general, it's not really going to make much of a difference because we are going to give these special names. They're called vectors. And in this particular case, it's called a 4 vector because there are 4 entries in it. You might have a 7 vector, which has 7 entries in it. In general, it really doesn't matter whether you write vectors as columns or rows, as long as there's a degree of consistency when you're doing your mathematical manipulation. Sometimes it's better to write them as columns or rows because it helps to understand what's going on, especially when we talk about matrix multiplication. But in general, both this and this are considered 4 vectors. So, okay. Let's see here. If m equals n. If m equals n. If the number of rows equals the number of columns, we call it a square matrix. Call it a square matrix. So something like A equals, let's say, 3, 4, 7, 10, 11, 14, 8, 1, 0, 5, 6, 7, 7, 6, 5, 0. So this is 4 this way, 4 this way. This is a 4 by 4 matrix. It is a square matrix. These entries, the ones that go from the A11, A22, A33, A44, the ones that have A, I sub j, where I equals j, those entries are called entries on the main diagonal. This is called, do this in red, this is the main diagonal from top left to bottom right. So the entries on the main diagonal of this square matrix are 3, 14, 6, and 0. And again, notice I haven't put the parentheses around them, simply because it's just my own personal notational taste. So you have a square matrix, you have entries along the main diagonal. Well, a diagonal matrix is one where every entry off of the main diagonal is 0. So something like, if I have A, I have 3, 0, 0, 0, 4, 0, 0, 0, 7. So notice I have entries along the main diagonal, 3, 4, and 7, but every other entry is 0. So this is called a diagonal matrix. A diagonal matrix is a square matrix where only the main diagonal is represented. Good. Okay. So let's start talking about some operations with matrices. Let me go back to blue here. The first thing we're going to talk about is matrix addition. So let's start with a definition here. Try to be as mathematically precise as possible. If A equals matrix entry ij, and the symbol here, when we put brackets, just one symbol with ij, this represents the matrix of all the entries I sub j. And if B is equal to the matrix B ij, are both m by n, then A plus B is the m by n matrix C Cij, where C sub ij equals A sub ij plus B sub ij. Okay, that is we get C by adding corresponding entries of A and B. So that's all this means. A big part of linear algebra and a lot of the lessons, the subsequent lessons, they're going to start with definitions. In mathematics, the definitions are very, very important. They are the things that we start from. And oftentimes there's a lot of formalism to these definitions. When we give the definition, we give them for the sake of being mathematically precise, and of course we do our best to explain it subsequently. So oftentimes the definitions will look a lot more complicated than they really are, simply because we need to be as precise as possible, and we need to express that precision symbolically. So that's all that's going on here. All that we're essentially saying with this definition is if I have a 3 by 3 matrix and I have another 3 by 3 matrix and I want to add the matrices, well, all I do is add the corresponding entries. First entry, second entry, and all the way down the line, and then I have at the end a 3 by 3 matrix. So let's just do some examples and I think it'll make sense. A equals 1 minus 2, 4, 2 minus 1, 3. So this is a 2 by 3 matrix, and let's say B is also a 2 by 3 matrix, 0, 2, minus 4, 1, 3, 1. So notice in the definition, both A and B are m by n, and our final matrix is also m by n. They have to be the same in order for you to be able to add them. In other words, if I have a 3 by 2 matrix, and if I have a 2 by 3 matrix that I want to add it to, I can't do that. The addition is not defined because I need corresponding entries. I need 3 by 2 matrix added to a 3 by 2 matrix, 5 by 7 matrix added to a 5 by 7 matrix. So addition actually needs to be defined. So they have to be the same size, both row and column, for addition to actually work. So in this case, we have a 3 by 2, so A plus B. I just add corresponding entries. 1 plus 0 is 1. Minus 2 plus 2 is 0. 4 minus 4 is 0. 2 plus 1 is 3. Minus 1 plus 3 is 2. 3 plus 1 is 4. And now I have my A plus B matrix. Just add corresponding entries. Nice and easy. Basic arithmetic. Okay. Now let's talk about something called scalar multiplication. Many of you have heard the word scalar before. If you haven't, it's just the fancy word for number, real number specifically. Okay, so let's let A equal the matrix A sub ij, again with that symbol. We'll let A be m by n, and R a real number. So we have a matrix A and we have R, which is a real number. Then the scalar multiple of A by R, which is symbolized R times A, is the, again, m by n matrix B sub j, such that the ijth entry of the B matrix equals R times the A sub ijth. In other words, all we're doing is we're taking a matrix, and if I multiply by the number 5, I multiply every entry in that matrix by 5. Okay, so let's say if R is equal to -2 and A is the matrix 4, -3, 2, 5, 2, 0, 3, -6, 2. Let's go ahead and put those. Then RA is equal to, well, -2 times each entry. -2 times 4, we get -8. -2 times -3, 6. -2 times 2 is -4. -2 times 5 is -10. -2 times 2 is -4. -2 times 0 is 0. -2 times 3 is -6. -2 times -6 is +12. -2 times 2 -4. This is our final matrix. Okay. Now let's talk about something called the transpose of a matrix. Okay. It's going to be a very, very important notion. It's going to come up a lot in linear algebra. So let's go ahead, transpose of a matrix. So we'll start with a definition. If A is equal to the A sub ij is m by n, then the n by m, notice I switch those, the n by m matrix, A with a little t on top, which stands for transpose, equals A sub j sub I. Well, actually, let me Tij, where, you write it down here, A sub ij, the ijth entry of the transpose matrix, is equal to A ji. Okay. So if A is an m by n matrix, then the n by n matrix A transpose is this thing where the entry is equal to the A sub ijth entry is equal to A sub ji, where the indices have been reversed. This is called the transpose of A. In other words, what we're doing here is we're just exchanging rows for columns. So the first row of A becomes the first column of A transpose. The third row of A becomes the third column of A transpose. And that's the best way to think about it. Pick a row and then write it as a column. Then move to the next one. Pick the next row, write it as the next column. That's all you're doing. You're literally just switching, you're flipping the matrix. So let's do some examples. So if A equals 4 minus 2, 3, 0, 5, 2, well, a transpose, so again, we're writing the rows now as columns. So I take 4 minus 2, 3, and I write it as a column. 4 minus 2, 3, and I take the next one, 0, 5, 2, 0, 5, 2. Now, what was a 2 by 3 has become a 3 by 2. Definition, m by n becomes n by m. That's all you're doing with a transpose is you're flipping it in some sense. So another example, let's say you have a square matrix. So 6, 2, minus 4, and 3, minus 1, 2, 0, 4, 3. Well, the transpose is going to be 6, 2, minus 4, written as a column, 3, minus 1, 2, written as a column, and 0, 4, 3, 0, 4, 3, written as a column. All I've done here is I've literally flipped it along the main diagonal, as if this main diagonal were a mirror image. I've moved the 3 here, the 2 here. See, the 3 is now here, the 2 is here. 0 went up to there, the negative 4 moved down here, this 4 moved there, the 2 moved there. That's all we're doing with a square matrix. But again, all you're doing is taking the rows, writing them as columns, and do it one by one systematically, and you'll always get the transpose that you need. Okay, let's see. Let's do one more for the transpose. So C equals, let's say, 5, 4, negative 3, 2, 2, negative 3. This is a 3 by 2, so I know that my C transpose is going to have to be a 2 by 3. Take a row, write it as a column, 5, 4. Take the next row, write it as a column, minus 3, 2. Next row, 2 minus 3, write it as a column, starting from top to bottom, and you get your C transpose. Again, all you've done is flip this. If we write a 1 by, let's say, 3, so let's say we have 3, 5, minus 1, this is technically it is a 1 by 3 matrix, so 1 by 3. So when we take D transpose, it is going to be a 3 by 1. 3 by 1, and it's going to be, well, 3, 5, 1. It's going to be that thing written as a column. But again, these ones where there are single rows or single columns, we generally call them vectors. We'll talk more about that specifically, more formally, in a subsequent lesson. Okay. So, let's recap what we've done here. We have a regular matrix. So, we're talking about matrix types here. Regular matrix, let me use red. It's just an m by n matrix of m rows and n columns. So, let's say we have 1, 6, 7, 3, 2, 1. This is 2 rows and 3 columns. This is a 2 by 3. A square matrix is n by n. That means the number of rows equals the number of columns. So an example might be 1, 6, 3, 2. 2 rows, 2 columns. Square matrices, very, very important, will play a major role throughout, particularly in the latter part of the course when we talk about eigenvalues and eigenvectors. A diagonal is a square matrix where all of the entries off the main diagonal are 0. So let's do a 3 by 3 diagonal matrix. So let's take 1, let's take 2, let's take 3, let's just put it along the main diagonal. Erase these random, and we put zeros in everywhere else. 0. This is a diagonal matrix. Entries along the main diagonal, zeros everywhere else. Okay? Okay, we did something called matrix addition, where the addition of corresponding entries in 2 or more m by n matrices of the same dimensions. Okay, so they have to be the same dimension in order for matrix addition to be defined. If you're going to take a 5 by 7, you have to add it to a 5 by 7. You can't add a 5 by 7 matrix to a 2 by 3 matrix. It's not defined because you have to add corresponding entries. Scalar multiplication. It's the multiplication of each entry of an m by n matrix. Oops. Erase these random lines again. So it's the multiplication of each entry of an m by n matrix by a non-zero constant. So if I have a matrix, could be 3 by 6, and I multiply it by 5, I multiply every entry in that matrix by the 5. The transpose is where you're exchanging the rows and columns of an m by n matrix, thus creating n by m. So if I start with a 6 by 3, I transpose it, I get a 3 by 6. If I start with a 4 by 4 and I transpose it, it's still a 4 by 4, but it's a different matrix because the entries have switched places. Okay. Let's go ahead and finish off with one more example of everything that we have discussed. So let's start off with matrix A. Let's go ahead and define that as 3, 1, 2, 2, 4, 1. And let's go ahead and put parentheses around that. Let's matrix B as 6, negative 5, and 4, 3, 0, negative 8. Good. So these are both 2 by 3. So certainly matrix addition is defined here. Let's find 2 times A minus 3 times B and take the transpose of the whole thing. So now we're going to put everything together. We're going to put addition, subtraction, we're going to put multiplication by a scalar, and we're going to put transpose all in one. Okay, so let's find 2A. Well, 2A is equal to 2 times 3, 1, 2, 2, 4, 1, and that's going to equal 6, 2, 4. 2 times 2 is 4, 2 times 4 is 8, 2 times 1 is 2. That's that one. Let's find negative 3b. So negative 3b is equal to negative 3 times b, which is 6, negative 5, 4, 3, 0, 8. And that ends up being, when I do it, I get negative 18, 15, negative 12. Actually, I'm going to squeeze it in here. I want to make it a little more clear, so let me write it down here. So I have negative 18, 15, negative 12, negative 9, and I hope you're checking my arithmetic because I make a ton of arithmetic errors. So this is negative 3b. So now we have 2a minus 3b. Well, notice this minus 3b is already, so we have this minus sign, we took care of it already. So this is the same as 2a plus the minus 3b. Okay? That means I add that matrix with that matrix. So when I add those two, I get 6. Wait a second, did I get this right? Let me double check. Minus 18, minus 18, this is 15, minus 12, negative 9, 0, minus 24, okay, that's minus 3b. Yes, okay, so 2a, so now let's add. 6 plus a negative 18 should be negative 12. 2 plus 15 is 17. 4 minus 12 is negative 8. 4 minus 9 is negative 5. 8 is 0 is 8. And 2 minus 24 minus 22. So this is our 2a minus 3b. Now if I take 2a minus 3b and I transpose it, I'm going to write the rows as columns. Minus 12, 17, minus 8, minus 12, 17, minus 8, and please check my arithmetic here. Minus 5, 8, negative 22. This is 2 by 3. This is 3 by 2. Everything checks out. This is our final answer. So we've got scalar multiplication, matrix addition, we've got the transpose, we have the diagonal matrix, which is only entries on the main diagonal, top left to bottom right, and we have square matrices, where the number of rows equal the number of columns. Okay, we'll go ahead and stop here for now, and we'll continue on with matrices next time. Thank you for joining us here at educator.com. We'll see you next time.